In this lesson, we'll use the concepts of regression and classification repeatedly, so let's first recall their definitions. A regression model is one that predicts a value, like 4, -3, or 6.7. In the graph on the left, we have drawn a line that fits the data closely. If we have a new value on the x-axis, we approximate it by finding the corresponding y value over the line. A classification problem is when one wants to determine a state, such as positive, negative, or such as yes, no, or cat, dog. In the graph on the right, we have some blue points labeled positive and some red points labeled negative, and we have drawn a line that separates them. If we have a new value in the plane, we guess its state based on which of the two regions it belongs. So to summarize, regression returns a numeric value and classification returns a state. So, now that you've built a model, how do you convince yourself and others that your model is good? You do this by testing. So let's look at the picture above, which shows a small regression example. Our data corresponds to the gray points. We have trained two models to fit the data. One is a line and the other one is a curve. Now the question is, which of these two models is better? Well, the one on the right fits the data perfectly, while the one on the left doesn't. So we're tempted to say the one on the right. To see how good the fit is, we can take a new point, this red point. The point seems to be well approximated by the model on the left, but is very badly approximated by the model in the right. So it seems that maybe the model in the left is better than the model in the right after all. What makes the model in the left better is that even though it doesn't fit the data perfectly, it generalizes better than the one on the right. The model in the right tries to fit the data too well, and it ends up memorizing it. This is called overfitting, and we will learn it later in the nano degree. Now the question is, how do we find a model that generalizes well? This is where we introduce the concept of testing. What we'll do here is we'll split our data into two sets, the training set and the testing set. In this figure, the training set is the set of gray points and the testing set is the set of white points. And now what we'll do is, as the name suggests, we use the training set to train the model, and then we test our results in the testing set. So here we have two copies of our set split into the training set formed by the gray points and the testing set formed by the white points. We can see two models that we trained on the training set, the gray points. Here the model on the right seems to be better than the model on the left. But once we test on the testing set, the white points, we see that the model on the left is much better, as the errors in red are much smaller. Thus we conclude that the model on the left is better, because although it performs a little less well on the training set, it does much better on the testing set. We can do the same procedure on a classification problem such as the one here. We have trained two classification models to separate the blue positive and the red negative points. This one on the left does okay as it only makes a few mistakes. This one on the right does great as it manages to separate all the points. But our intuition tells us that the one on the left may be better as it is more general. Meanwhile, the model on the left treats these outliers as noise and it tries to fit the data in a simpler and more general way. So in order to pick a good model, we'll take some points and call them the testing set. The training set is then given by the points that are filled in, while the testing set is given by the points that are not filled in. Now we train the two models. Notice that the two models fit the training set well. But once we introduce the testing set, the model on the left only makes one mistake, whereas the model on the right makes two mistakes. Thus, by testing, we conclude that the model on the left is better. The way to do this in sklearn is very simple, using the function trainTestSplit from the model selection package. First, we import trainTestSplit. The trainTestSplit function takes the following as arguments: the input, the output, and the percentage of data we want to leave as testing data. For example, test size equals 0.25 means that 25% of our data will be used as testing. In this example, we have 16 data points, so 4 of them will be used as testing data and the remaining 12 as training data. Now there is a golden rule that we must never ever break. The rule says, thou shalt never use your testing data for training. This is very important. When we select some data for testing, we must put it aside and not look at it until the very end, and we should not use it to train the algorithm. This rule is actually very easy to accidentally break, and you'll see why very soon.